Ever tried predicting the weather and ended up with a range, like 30–60% chance of rain, instead of a single answer? That's the essence of uncertainty in science and AI. Today, we're exploring a powerful framework called Dempster-Shafer theory, which tackles these fuzzy probabilities when exact numbers are elusive. Let's dive into how it reshapes our approach to uncertainty. Imagine building a medical diagnostic model. Traditional methods like Bayesian networks rely on exact probabilities, but what if the data is sparse or conflicting? That's where credal networks shine. They're like Bayesian networks with a twist. They handle imprecise probabilities by expressing outcomes as ranges, not fixed values. Instead of 30% chance of rain, you might say 20–40%, a safety net for uncertainty. But here's the challenge. Credal networks are computationally heavy. Even simple setups demand intensive calculations. Enter Dempster-Shafer theory, or belief functions, a mathematical framework that doesn't just manage probabilities but uncertainty about probabilities. It's like a toolbox that says, I'm not certain but I know it's within this range. Now let's break down credal chains, a simpler type of network where each node depends only on the one before it. These are ideal for testing. The study we're examining translates uncertain probabilities into belief functions, enabling conservative intervals, safe estimates that err on the side of caution. It's like saying, we're confident the answer lies in this range, and we'll never be wrong about it. The beauty. This method leverages existing tools, speeding up computation. But there's a trade-off. Intervals can become too wide for practical use. It's like using a sledgehammer to crack a nut, efficient but not always precise. The paper also compared this to sensitivity analysis, which tests how input changes affect outcomes. The verdict. Belief functions are fast and robust, but sometimes sacrifice tight bounds. So what's the takeaway? When exact computation is impossible, belief functions are a lifeline. They protect models from ignoring worst-case scenarios, whether it's weather forecasts, medical diagnoses, or self-driving cars. They're the backup plan for uncertainty, ensuring predictions don't overlook surprises. Thanks for watching. Uncertainty isn't a flaw, it's a reality. With tools like Dempster-Shafer theory, we can navigate it with confidence. Stay curious and we'll see you next time. Ever wondered how scientists handle uncertainty when data is shaky? Think of a weather app saying, 30% chance of rain. That number feels concrete, but what if the data is conflicting? Enter imprecise probabilities, a math upgrade for handling uncertainty flexibly. Let's unpack it with a simple example, flipping coins. Traditional probability assigns equal weight to all outcomes, but researchers found a smarter way. They use ad-hoc mass functions. Think of them as spotlights that zero in on the outcomes that matter. For instance, tracking 4 coins, you might ignore complex combos that don't help predict the next flip. This keeps results tighter and more accurate. Here's the kicker. In tests, this method improved prediction accuracy by up to 30% compared to old-school techniques. Imagine being 30% closer to the real answer without wild guesses. It's not just for coin flips. When tested on chains of dependent events, the ad hoc approach outperformed traditional methods. For binary cases, belief intervals shrank by 40%, and after one inference step, precision jumped 19%. But there's a catch. If your starting data is too vague, even these tools struggle. That's why scientists are now testing them with narrower real-world data, like weather patterns or medical stats, where probabilities aren't all over the place. So why does this matter? It means we're better at navigating uncertainty in AI, climate models, and everyday decisions. These tools balance accuracy and reliability, helping us make smarter choices. Stay tuned for the next part, where we'll see how they hold up in real-world scenarios. If you found this intriguing, hit that like button and subscribe for more deep dives into probabilities mysteries. Until next time, whether it's weather forecasts or medical diagnoses, the math behind uncertainty is shaping the future. From Dempster-Shafer theory to ad hoc mass functions, these tools are rewriting the rules of prediction. Keep exploring and remember, in a world of unknowns, clarity is the ultimate innovation.